All right, are you ready to play Family Feud? Period 7, send up your best contestant. Period 8, send up your best. All right, looks like period 7 has sent up pi, and period 8 is coming at you with infinity. Contestants, we asked 100 people the following. All exponential growth and decay patterns will fit what model? Pi. Percent. Is it percent? It looks like period 8 has a chance for the steal. So infinity. What do you think? All exponential growth and decay patterns will fit what model? Y equals AB to the X. Is it Y equals AB to the X? It looks like we have a winner. And the winner is Y equals AB to the X, which is always seen in percent growth and decay patterns. Now for today's lesson, we're going to find out just how. So period 7, period 8, you both make it to the final round. Now the final round is to figure out just how we apply this exponential model to percent growth and decay patterns. So recall with me one more time that all exponential, that is percent, growth and decay patterns will fit into this model, y equals a b to the x. It's such a simple formula, but it's so powerful because it will allow us to apply all percent change models. Now, maybe it'd be helpful just one more time to take a look at the numbers that are seen in this equation. Because what I want you to realize is that it's all about the base, the base, the base. Now, when you look at that base of 1.6, everybody needs to say that this is a growth problem. Because, as we've said a number of times, that number, 1.6, is greater than 1. Now, how much greater than 1? What do I mean, how much greater than 1? Well, it's the 0.6, which is actually the same as 60%. That tells us how much growth we're going to have. You see, we're going to have 60% growth when the base is 1.6. So how about this other one over here? How about this base? Well, I think it's pretty clear that the base is less than 1. And because the base is less than 1, this is going to be a decay problem. But how much less than 1? How much is 0.8 less than 1? Well, it's 0.2. 0.2 is the same as 20%, which really means that this equation is going to represent 20% decay. So the base tells us how much growth or how much decay, and it's always related to the number 1. So what we're going to do is take our equation, y equals ab to the x, and we're going to elaborate on it a little bit. We're going to modify the variable slightly to better match an application problem. Now, we're going to write it as y equals a. We'll still use a as our starting value, but the base is now going to be described as 1 plus or minus r. And then we will make the exponent be the letter t. So how do these new variables match with an application? Well, I think you'll find they match quite nicely. First, we have our y equals, which in almost all cases in math, when you look at a formula, that will be the final value. That will be the final value. Versus a, which we will use as our starting value. Now, the main part of this formula, the main new part of this formula, is what has happened on the inside, what has happened here to the base. You see, the base has now been described as 1 plus or minus r, where r is going to be our growth or decay rate. R is going to be the percent. And so as you can see, the percent is being added or subtracted from the number 1. And so if it's going to be growth, we would add, and if it's going to be decay, we're going to subtract. Now make sure you always change that percent to a decimal, one of those good habits when it comes to math. And then look at our exponent. Our exponent is t, which makes perfect sense to be described as time. And you see it can be any type of time. It could be minutes, days, years. It just has to match the percent change. And so our exponent t will be time. Our first problem is going to be a classic example of having an initial value and a rate. And these types of numbers fit perfectly into our exponential model. So let's say we have an investment. That would be like money that we decide to put into a savings account, and it increases at 12.5% every year. Now, that is a lot of money to stick into a savings account, but let's say you are able to do that for 30 years. Well, those numbers are going to fit perfectly into our y equals a, 1 plus. We're going to use plus because this is definitely a growth scenario, 1 plus r to the t. So we just want to identify 75,000 as our starting value. We definitely are going to take 12.5% and use that as our rate. And of course, 30 will end up being t. So when you plug all those numbers in, you end up with y equals 75,000, 1 plus. Now be careful. You want to change 12.5% to a decimal by moving the decimal place 2 places to the left. So definitely we end up with 0.125. And so all of that is raised to the 30th power. Now, most of this ends up just being a calculator problem, but I always recommend that you do simple math before you get your calculator out, and in this case, simple math would be to definitely add 1 plus 0.125 so that we get a base of just 1.125. Now, a lot of the calculators that you have are able to handle this formula in one step, as long as you very carefully use the exponent key. On some of your calculators, the exponent key is going to look like this caret top button. On some of your calculators, it's going to look like a y to the x button. And make sure that you just know your calculator so that you can type in the exponent. On my calculator, it's going to look like this, where I can type in 75, 1.125 raised to the 30th power. And we end up with this really big number, 2.5 million. Yes, you would have $2.5 million. Now, if you have a calculator that requires you to do computations in 2 steps, then you're going to want to definitely do the exponent first. You're going to want to do 1.125 raised to the 30th power and hit enter. Now, once you get that number 34, all you have to do is multiply it by 75,000. And so we followed the order of operations very carefully to get the same answer, 2.5 million. Now, as I said in the preview, make sure that you actually are doing these problems on your calculator. Don't just watch me do them, so that you can get them right when it's time for you to do them on the back. Now, our next problem, it's not going to be quite as easy as the first, because as you'll discover in a moment, it takes a couple steps and some algebra to get to our final answer. But it's still a classic example of the exponential model, because as you can see here, we have a population that is decreasing by a percent, specifically 1% per year. Anytime you have a change, a percent change, it's always going to fit into the exponential model. Now I'm going to choose for this problem to start by just setting up the base, because I want you to see real clearly here that the base is going to be represented by a 1 minus. Since it's decreasing, we're going to choose a minus sign. Now, you always change percents to a decimal, and 1%, when you move the decimal 2 places to the left, will be written as 0.01. So now we have 1 minus 0.01. Now, as you read on through the rest of the problem, you see here that after 50 years, there's only 121,001 birds remaining. And the question is, what was the original population? So we want to be real careful here to understand that what we're really trying to find is A. In other words, we don't know the starting value. We don't know the original population. So what are we going to do with 50 and 121,000? Well, those two numbers will represent our final value. So we'll put 121,001. We'll put that in for the final value. And we will put well, I'll tell you what, I'm going to go ahead and subtract 1.01 to be 0.99. Anytime you can do some simple math, do it. But what I want you to see is that we're now going to use 50 as our t value. And so these two purple numbers, I like to say that they're like matching numbers. After 50 years, we end up with 121,000. And so those two numbers would represent like a point. And a nice thing about having those two numbers plugged into the equation is now we only have one variable left, and that is A. Now, do you understand that you're actually going to have to do some solving here? You can't just plug all this in your calculator. But this value, this 0.99 to the 50th power, that can be calculated. And after you calculate it, all you have to do is divide it over here to the other side. So if you do those steps on your calculator, you would first take 0.99 to the 50th power. You probably get some strange decimal. I encourage you to round it to at least 3 decimal places. Now, 0.605 is going to simply be divided to the other side of the equation. And so when we divide it, we end up with our final answer. Showing your work, which I would expect you to do, we can show that we get A times this new value here, this 0.605 number, and in dividing that over to the other side, we end up with our final answer, which actually is our initial answer, I suppose. It's our initial value of 2,000, and don't forget that one bird. Maybe it rounds up to 2,000 and 200,002 birds, but generally we have about 200,000 birds that started out in this population. Now, as we flip over to the back, we're going to look at our last example, which you're going to discover shortly does not give us a percent. Oh no, it doesn't give us a percent. Instead, it gives us 2 data points. Now, what do you suppose we will do if we are not given a percent? Well, that's correct. We're going to have to find the percent. We're going to have to find the percent. Now, I warn you against trying to do this by just plugging some numbers into your calculator and hoping for the best. Instead, what we're going to want to do is we're going to want to use the exponential model. Now, the exponential model has come to us in 2 forms. It's come to us in this original form, this simple form, ab to the x. But I want you to realize from today's lesson that we can also describe that using the form y equals a 1 plus or minus r to the t. So we can talk about the exponential model in 2 forms, and it depends on the problem as to which one we will choose to use. You're going to find out for this scenario that we're actually going to want to choose the simple form. All right, so what do we have here? We have a truck that is decreasing by a certain percent. Now notice that we don't know what that percent is, okay? But we do know that after 1 year, the truck is worth $25,000. And after 4 years, the truck is worth $18,000. So what we want to do is try to write an exponential model and figure out what the percent is. Now, Whenever we plug numbers into the exponential model, we always have to think about what it is that we're given. And I'd like to help you realize that what you're actually given here are two data points. You see, we could say that 1 matches with 25,000. And when two numbers match, they can be written as a point. And you see 4, well, it matches with 18,000. And same thing, when numbers match, we can write them as a point. Now, what we're going to do is we're going to take these numbers and we're going to plug them in to y equals ab to the x. And when we plug in, we're going to ever so carefully use the point as our x and y. So would you agree with me that I could use 25,000 as my y value? Now notice I don't know what the starting value is, and I don't know what the base is, but all of those things are okay. Now I do know what x is, since I'm plugging this point in for x and y. I can plug a 1 in here for x. Now, this equation might seem a little strange to you. It might seem like it doesn't tell us much, but I beg to differ, because what it can tell us is what the value of a would be based on our formula. Let me explain. If we divide both sides by b, we are able to describe a as an expression. The expression 25,000 divided by b equals a. Now, why would I want to do that? Well, when it comes time to go over here and use my second point, I'm talking about the point 4, 18,000. I can also plug that into this equation, where I will plug 18,000 in for y, and we'll plug 4 in for x. But the neat thing about this scenario is we will also have something to plug in for a. And what will we plug in for a? Well, we will plug 25,000 over b. Now, there's a lot of arrows pointing here, I know. So let's kind of do one thing at a time. We're going to plug 18,000 in for y. We're going to plug 25 over b. We're going to plug that in for a, because that's what we found out when we solved that is the same thing as a. Now, I still don't have anything to plug in here for b. That's fine. I don't need to plug anything in for b because, as you'll discover, I don't know what the base is. But I do have something to plug in for x, and that is this number 4. So what we're going to do is we're going to put a 4 in here for x. Now, this equation, I know it might have been a little complicated to get here, but this equation, let's get rid of this line in the middle, has one variable. And anytime you have one variable, you're always able to solve. And so what we will do now is we will carefully solve this equation for b. Now, in solving this for b, there's something to note, and that is that we have some b's that can cancel. You see, we have a b to the 4th, and we're dividing it by a b. And so the rules of algebra say that those will cancel to leave us with just a b to the 3rd. So again, we cancel the exponents so that we can end up with just b to the 3rd. The rest of the values do stay put, and now we're getting closer and closer to being able to solve this for b. Actually, the only thing left to do is to divide both sides by 25,000, and then we're going to need to undo this b to the 3rd. We're going to need to undo this exponent. So let's divide both sides by 25,000. That ends up giving you a number that's close to 0.741. Again, when I divide both sides. Now, we have one more thing to do. We have to undo this exponent. We haven't talked about this too much, but it is true that a root will always cancel with an exponent. It's just that we want to use the same root. So if this is a b to the 3rd, we're going to have to use a matching root of a cube root. So what I'm doing is the cube root of both sides. And what that does is it cancels with my exponent. and it finally leaves me with the base. Now, that comes out to be 0.905. Now, I understand you might be asking, whoa, Mr. Naylor, how did you do this on your calculator? So let's take a look. First, I divided both sides by 25,000, and that gave me that 0.741 number. I did choose to round it to 3 decimal places. Now, the key to this problem is doing the cube root of both sides. To do a cube root, you have to find the cube root command on your calculator. Everybody's calculator is going to be a little different, but here's the thing. It's not a square root. It's a cube root. And some of your calculators, that might be in a menu. It might also be a button on your keypad. But you want to look for the cube root, not the square root, but the cube root, so that you can do the cube root of 0.741. Some of you will find an X root button. If you use the X root button, you actually first want to type the number 3 on your keyboard, and then you will activate the X root button. And what happens is the number 3 will get inserted in here for this root. Okay? So we do the cube root of both sides, and we get 0.905 if we round that to 3 decimal places. Now, I told you this problem's a little bit harder. We're not quite done, but we're almost there. The question was, could we write an exponential model? Well, what I want you to understand is that yes, we can, because now we have the base. And whenever you have a base, you can always write y equals a b to the x. So we wrote our exponential model by filling in the base as 0.95. Now, I think the question also said, what would be the percent decay? What would be the percent decay? You want to realize that we haven't found it yet, but we're only a subtraction away. Because as we've talked before, this base of 0.95 is actually the same thing as 1 minus a rate. And so the question really becomes, what rate would I subtract from 1 to get 0.905? Well, all you have to do is subtract 0.905 from the number 1, and you'll find out that you end up getting 0.095, which actually represents 9.5%. And so for this situation with this truck, it is losing 9.5% every year. And we found that by very carefully plugging in these points so that we could solve for B. So that once we have B, which remember, B was 0.905, once we have that number, we can find R. And R would be the value that we subtract from 1 to get that base. Now, had we been in class, this would be one of those activities where I would want you to get each problem correct before moving on to the next. Mr. Naylor probably would have walked around and signed these before allowing you to move on to the next activity. So what we're going to do for our online learning is we're going to use the Google form that I created to allow you to test and to check each one of your answers before moving on to the next question. Now, the way the Google form is designed is that it's going to force you to go back until you can get the right answer. And the idea is to get the right answer for 1, 2, and 3. I want you to get full credit for this activity. Now, I'm going to do this for number 4, or for this problem up here, we'll call it number 4. We're going to make it bonus. It's a little challenging because it's kind of like this problem over here, but just the same, I'd love you to try it because I think you can also get this one correct. So use the Google form to test and check that last answer. We'll call this one number 4 and see if you can also get that one right.